But we can use our calculus to figure out the length of any curvy object. So we're going to be looking at functions that aren't circles when we talk about our arc length. So we're going to use integrals, and we are going to integrate basically the distance formula, but we're going to kind of calculusify it, if that's a word, which it isn't. So on this slide, this is getting us to where we are going to get our integral, and then over here on the side, I'll write what our integral for arc length is. But at the start up here, we see the distance formula as we know it. So the square root of x2 minus x1 squared plus y2 minus y1 squared. Then we can kind of get fancy. If we take the difference between the two x's, we can call that the change in x, which we could denote as delta x. Now we're going to integrate with respect to x, so that's where our delta x in the bottom is coming from. And then similarly, we have our y2 minus y1, so we're going to get our change in y. And then again, with respect to x, because that's how we're going to integrate. It doesn't technically work this way, but it's going to be this way. It's going to work essentially where delta x divided by delta x is equal to 1. So 1 squared is 1. If you take differential equations, which is basically calculus 4, you'll talk about why we can actually do that. It's not really dividing something by itself because that's telling us we're doing something, but essentially it's the same thing. And then we know that delta x over delta y is just another fancy way of saying f prime. So what we're going to integrate is the square root of 1 plus f prime squared. So our arc length formula is L is equal to the integral from a to b, so whatever interval we're on, of the square root of 1 plus f prime of x squared with respect to x. Now, most of the time we're going to be integrating with respect to x. Sometimes it'll be with respect to y. The only thing that would change is your delta x's would turn into delta y's. So this would be the 1, and this would be dx dy, which would be x prime instead of y prime, and that would be dy. And we'll see an example of that. I think it's our third example. But this is going to be what we need to know. This is our arc length formula as far as our calculus is concerned. So let's jump in. Let's take a look at this problem here. Find the length of the following curve on the given interval. So I like to kind of take this a little piece by little piece. I don't like to put everything in my integral until I'm absolutely ready for it. And you'll see why here momentarily. And it works this way, at least for all the problems that I've done from the homework. I don't usually do all of it. But it works this way for everything. So simplifying as much as we can before we get into our integral is going to be very useful. So when we look at our y here, we're going to need to use our chain rule to take the derivative because we have something inside parentheses raised to a power. So when we go ahead and figure out our derivative, we can say y prime. We have that 1/3 out front, so now we can start our derivative here. So we're going to take our 3/2, drop it to the front. We're going to keep the inside parentheses the same, so x squared plus 2. We're going to decrease by 1, so that'll be a 1/2. And then we need to multiply by the derivative of the inside, so the derivative of x squared. So the first thing we're going to do is try to simplify some stuff here. So we have a 3 and a 1/3, so those things can cancel. We have this 1/2 here and this 2, so that can cancel. So our derivative can be simplified into x times the square root. I'm going to put this back into square root here, and you'll see why in a second. So there's our y prime. Now, if we think back to what we were supposed to take the integral of, we're supposed to take the integral of the square root of 1 plus y prime squared. So let's go ahead and square this. And that's why I put it back in the square root. For me personally, when I'm doing algebra, I like to see roots instead of powers. For whatever reason, squaring a square root is easier in my mind than squaring a 1/2 power. You don't have to do it that way. That's just the way my brain works. So if we're going to square this thing, it's just a product, so we can square both pieces. So we're going to get x squared from the first part, and then the square root of x squared plus 2 squared is just going to give us x squared plus 2. And let's go ahead and distribute our x squared. So we're going to get x to the fourth plus 2x squared. All right, so we also need to add a 1 to that. I forgot to say that that was squared. So that's just a simple x to the fourth plus 2x squared plus 1. And here's where our lives are hopefully going to be getting much simpler here. Because remember, we have to take the integral of this, the square root of this thing. Now, every problem that I've done, when I get to this point, it's going to factor into a perfect square. And this factors into x squared plus 1 squared. So if you do a quick distributive property in your mind, x squared times x squared gives us x to the fourth, x squared times 1 gives us x squared, 1 times x squared gives us x squared, which is that 2x squared, and then 1 times 1 gives us 1. So that's our 1 plus y prime squared. And then if we take the square root of 1 plus y prime squared, we get the square root of x squared plus 1 squared, which is just going to be x squared plus 1. So that is ultimately what we want to integrate, because that is 1 plus y prime squared. So we're going to go ahead and say our length is equal to the integral from 0 to 9 of our x squared plus 1 with respect to x. So it can't get really any easier than that. Integral, right? So increase to 3, divide by 3, so we're going to get a 1/3 x to the third plus x, evaluated from 0 to 9, and that is going to give us 252. All right, so that is our first problem. Nothing too crazy going on there. This next one, for whatever reason, there's a bunch of problems like this on the homework, and they're not necessarily any more difficult. They just look a little goofy because we have this x to the third in our denominator. So before we start taking a derivative, I'm going to rewrite this as 1/5 x to the fifth plus 1/12, not 12, but how about 1/12 x to the negative third power. That way I can use power rule and don't have to worry about quotient rule. So now we just kind of take the same process that we had a second ago. We'll start with our derivative. So drop our 5, that's going to cancel. We're going to get an x to the fourth. Drop our -3. -3 over 12 is going to give us a -1/4. And then this is going to be x to the -4th. And this is what makes this one a little bit goofier than the other one, because we have like x to the fourth and x to the 1/4. It's nothing that we can't handle. It's just a little ugly. So if we go ahead and square that, we're going to get x to the fourth times x to the fourth is x to the 8th. And then we would have x to the fourth times -1/4 x to the -4th. So our fourth and -4th powers are going to cancel each other out. So we're going to get x to the 0, which is just 1. So we're subtracting 1/4. And then when we do it the other way, we're going to get another -1/4. So that'll be a -1/2. And then plus 1 over 16 x to the -8. So if that doing that without actually writing it out was a little bit tricky, and you're like, where did that negative one half come from? Just throw some parentheses around this thing, put another set of parentheses next to it, do the distributive property, combine your like terms, you'll end up here. So now we want to add 1. So 1 plus y prime squared. Negative 1 half plus 1 is going to be a positive 1 half. And usually when we are writing out a polynomial, we'll put our 1 half at the end because it doesn't have a variable. But if we keep it in the middle, it's going to help factor a little bit more. But the good news is when we go to factor this thing, I want to say always, but I don't ever say always. So I'm going to say almost always because there's bound to be an exception. But almost always, it's going to be the conjugate of your derivative. So this is going to turn out to be x to the fourth plus 1/4 x to the negative fourth squared. And we can do a real quick check just to make sure that this works. And I would check it. So x to the fourth times x to the fourth gives me x to the eighth. When I do x to the fourth times 1/4 x to the negative fourth, again, our 4 and negative 4 cancel, giving me just a plus 1/4. Do it the other way, another plus 1/4, which gives me the plus 1 half. And then this term squared gives me that. So we are good to go as far as that factoring goes. So again, let's take our square root. And this will be the last time that I actually write the square root squared. We're just going to simplify it in the future. So 1/4 x to the negative fourth squared. And then again, our square and square root are going to cancel each other out. So we're going to be just left with, that's a fourth power, like marker. I guess computer, not really marker. It's kind of laggy. All right, so once again, we have a pretty straightforward, not so crazy integral. I guess I probably should have looked at my interval before I went to here. We're going 1 to 3. So we're going to integrate x to the fourth plus 1 half x to the negative fourth with respect to x. Ooh, why is it doing that? That was weird. I picked the marker up or the pen up and it went crazy. Equals. All right, so 1/5 x to the fifth. Increase that to negative 3, so minus 3/4 x to the negative third. Oops, sorry, not negative 3/4. I took a derivative. We would divide by negative 3, giving me negative 1/12 x to the negative third. I apologize for that. And then we're evaluating from 1 to 3. And that's going to give us a totally not ugly fraction at all. I don't know what's going on with the marker here. 39,269 over 810. So, not an ugly answer at all. All right, so we had a pretty straightforward one. We had still kind of straightforward, but a little ugly because of our negative exponents. We have 2 left. This next one is basically the same thing that we just did, but now we are going to be integrating with respect to y, and we can see that because the curve is x equals. So literally the only thing that changes is we have x prime instead of y prime here. So let's go ahead, just like we did a second ago, and let's rewrite x to where it's going to be easier to take the derivative. So 1/9 y to the third plus plus 3/4 y to the negative 1. All right, so we can go ahead and easily take that thing's derivative. So x prime is equal to, so 3 drops down, we get 1/3 y squared. Drop our negative 1, so that'd be minus 3/4 y to the negative second. And we got to square it. All right, so our process doesn't change. We're just dealing with our function written in terms of y instead of x. So we're going to get a 1/9 y to the fourth. Negative 3/4 minus 3/4 is going to give us a. I'm sorry, we don't have 3/4 because we have that 1/3. So 1/3 and times 3/4 is 1/4. So we get negative 1/4 minus 1/4 is negative 1/2. And then plus 9/16 um, y to the negative fourth. All right, we'll go ahead and add 1 to that. And that's just going to make me angry. Sorry. That's just going to turn this negative 1/2 into a positive 1/2. Don't know why that keeps doing that. 9/16 y to the negative fourth. All right, so we can factor just like we did before. And it's going to turn out to be, just like I said before, this thing right here, our x prime, but the conjugate. So it's going to be plus instead of minus. So we're going to get 1/3 y squared plus 3/4 y to the negative second squared. And then when we take the square root of the stuff, ugh, we're going to get the 1/3 y squared plus 3/4 y to the negative second. And that's where we would take our integral. Nothing crazy goes on there. I'm going to leave that up to you. So I'm just going to let you know that our answer should be 989 over 90. So go ahead and work that out and see if you get what you should be getting there. All right, so the last thing that we're going to look at is going to be something that looks absolutely crazy, absolutely off the wall, but it's not going to be bad once we remind ourselves of something from Calculus 1. So find the length of the curve below on the given interval. X equals the integral from 0 to y of the square root of 2 secant to the fourth t minus 1 dt. So this is really wild looking, right? So our function is actually an integral. And in that integral, I don't know why I'm rewriting the function. I'm not going to rewrite the function. In our integral, one of our limits of integration is a variable. But if you think about our process here, we need to take the derivative of that. So we get this thing called the fundamental theorem of calculus, which you may or may not remember. But what the fundamental theorem of calculus says basically is that derivatives and integrals cancel each other out. They're inverse operations. Just like squaring a square root is going to give us what's on the inside, the same thing is going to work when we take the derivative of an integral. Now, the one thing that kind of changes is if our limit of integration that is a variable is anything other than just x or y, then we have to multiply by the derivative of that limit of integration because of our chain rule. But since it's just y, the derivative of y is 1. So all we need to do here is take that y, plug it in here for t, and that's our derivative. So our derivative is the square root of 2 secant to the fourth of y minus 1. Now, lots of good things are going to happen here. So the first thing we want to do is square our derivative. And again, get frustrated and not know why things are working the way they are with my pen this morning. So when we square that, our square root goes away. So we just get 2 secant to the fourth of y minus 1. And then when we add, I'm just going to put plus 1 because my computer's being weird. That's going to go away. So we get 2 secant to the fourth of y. Then we need to take our square root, which is going to give us the square root of all of this stuff. Now, what we can do with a square root that has a product in it, we can take the square root of the first piece and multiply it by the square root of the second piece. So when we do that, we're going to get the square root of 2 times secant squared of y. So let's go ahead and finish this one out. So our arc length is going to be equal to, I can pull out my square root of 2, integral from negative pi over 6 to pi over 6 of secant squared y dy. Now, if you remember, secant squared is a nice antiderivative. It's just going to be tangent. So we're going to be looking at the square root of 2 times tangent. If I can write it kind of in semi-cursive, that messes up less, of y. And then it takes a while to write that, so I'm just going to assume that we know what our limits of integration are here. So what we're going to be looking at then is the square root of 2 times, so tangent of pi over 6 is going to be 1/2 over square root of 3 over 2. So that's going to be 1 over the square root of 3. And then minus the tangent of negative pi over 3, which is negative 1 over the square root of 3. So negative, or 1 over square root of 3 plus 1 over square root of 3 is 2 over the square root of 3, and then we have a square root of 2. So we can call that 2 square root of 2 over the square root of 3. So that is going to be it for this video, and we'll see you in class.